Okay, this is part 2 from the semester's exam 2. It says, what work must you do to move a 5 microcoulomb charge from point A to point B against forces from the dipole consisting of opposite charges, Q1 and Q2? So you have these two charges here, Q1 and Q2, and you're trying to find the work it would take to move a 5 microcoulomb charge from point A, which is here, to point B here. So the work to move from A to B is the charge that you're moving times the potential difference between A and B. So you're moving 5 microcoulomb charge, so you know that, and the potential difference is what you don't know yet. So you need to know what is the potential difference between here and here. So the potential, say let's choose this point first, point A. The potential at that point is the sum of the contributions to the potential from each of those two charges. So this has a potential of plus kq1 over r, where r is the distance to this point here. And this one has an opposite contribution, so minus k q2, where q2 is 1 microcoulomb also, over r2. And then we'll do the same thing for point B and find the potential at point B, and the potential difference we'll multiply by the charge to get the work. So the potential at A we'll find first. This is K times Q1 over R1 plus K Q2 over R2, where R1 is the distance from here to here. So let's see, this is 2 centimeters, and the distance from here to here is 4 centimeters. So this is K times 1 microcoulomb over 2 centimeters plus negative 1 microcoulomb over 4 centimeters. Potential at B is going to be similar, so K times, if you're at this point, the contribution from the positive charge is now plus 1 microcoulomb over this distance is 6 centimeters, 4 centimeters. So this is over 4 centimeters minus the contribution from this one, 1 microcoulomb over 2 centimeters. So if you do this and subtract the two, you get a potential difference of VA minus VB is 4.5 times 10 to the 5 joules per coulomb. I'm sorry, negative 4.5 times 10 to the 5 joules per coulomb. And so if you multiply that by the charge, so you found the potential difference, if you multiply that by 5 microcoulombs, you get that the work is negative 2.25 joules. Okay, so part B here. Part B was kind of a tricky one. So it says we have a Van de Graaff generator to put a large amount of charge on a 5 centimeter radius metal sphere, and that pushed charged styrofoam pieces upward against gravity. So you have, the situation is that you have this sphere, the 5 centimeter radius, and it's held at some electric potential V. So it's got some charge built up on it. And this is causing an electric field radially outward. So we're going to put charged pieces in this electric field and cancel the force of gravity on those pieces. So we'll end up putting our styrofoam up here, and the styrofoam will have a charge on it, and the force on this charge on the styrofoam due to the electric field of this sphere is going to cancel gravitational force, and so the styrofoam will float. So the equation for potential of a sphere is K Q of a charged sphere is kq over r, where r is the radius of the sphere. And the electric field for points outside of the sphere is kq over r squared, so the electric field at some distance r away. So if we put our piece of styrofoam some distance, this is 5 centimeters just from the center to the outside, plus it says 2 centimeters up, and then plus another ½ centimeter to get to the center of the styrofoam, we're going to put our charge at a distance of 7.5 centimeters away. So the force on our styrofoam is going to be the charge on the styrofoam times the electric field at a distance of 7.5 centimeters away. So that's, the charge on the styrofoam was 15 nanocoulombs, and the electric field 7.5 centimeters away is k q, this is q of the on the Van de Graaff, over 7.5 centimeters squared. Okay, and we want this force to cancel the gravitational force on the styrofoam. So we have this electric field, or the force due to the electric field pointing up, and force due to gravity pointing down. So this is going to be equal to mg, where m is the mass of the styrofoam. So now what we need, we know all this stuff. We know everything other than q in this equation, the charge on the Van de Graaff. So we can use this to find q, and then put q in here. Q is the charge built up on the Van de Graaff sphere. So then we can relate it to the potential on the sphere with this equation. So the equation for the potential of a sphere. So if we do that, we get that well, let's just try and combine these two equations. So we had that V, the potential is kq over big R, and force is equal to small q, so q of the styrofoam, kqq over r squared, and this is also equal to mg. So if we multiply force by big R and divide by R, so we haven't done anything, then we can see that the force is equal to this k big Q over big R is the potential. So force is equal to the potential of the sphere times little q, big R, and let's see, kq over R is V, so V big, yep, and then over little r squared, and this is equal to mg. So now we can solve for this. This is what we're looking for, is the potential, and these things are known. So if you do that and you solve for potential, then you get 83.627 kilovolts. All right, part C here is to find the resistivity of a piece of copper at room temperature. So it's 18 gauge wire, has a diameter of 1.024 millimeters, and you want to know the resistance of a 10 meter length of 18 gauge copper wire. So the resistance of a wire is the resistivity of the metal that it's made out of times the length of wire that you have, and then divided by the area, the cross-sectional area of the wire. So this is, if you have a wire like this is the length of it, some distance L, and the cross-sectional area here. And the resistivity is just the property of the copper. So let's see, what do you know? Resistivity of copper is 1.68 times 10 to the minus 8 ohm meters. So that's from here. The length was 10 meters of wire, and the cross-sectional area is pi times the radius which is 1.024 millimeters over 2 squared. And if you do that and convert millimeters to meters, then you get 0.204 ohms. Okay, and part D. So for part D, you're asked to find from this graph what are the values of R and C for this circuit. So you have an RC circuit, the switch closes at time t equals 0, and this is a plot of the current through this circuit. So it starts off at a high value, and because the capacitor was initially uncharged, and then as the capacitor charges up, more of this voltage is dropped across the capacitor and less current flows through this resistor or through the circuit until eventually the capacitor is all charged up to the battery voltage and 0 current flows. So to find the values of R and C, you have to do two things. So you can look at what the initial current is. So initially, right when you close this switch, the capacitor is effectively a 0 capacitance, and so you just have a 10-volt battery across this resistor here. So if you do that, so initially you have this equation. So you have 10 volts, and this is across the resistance that we're trying to find, and your initial current is 250 microamps. So this allows you to find R at the very since the capacitor doesn't matter initially. So if you do this, you get a resistance of 40 kiloohms. And so now you're left to find C. So you can find C because you know that the RC time constant of this RC circuit is just the resistance times the capacitance. And the RC time constant is the time it takes for the current in the circuit to drop to 1 over E of its initial value. So you start off at 250, it drops to 250 over E at some time when t equals this RC constant. So if you find 250 microamps over E is 92 microamps, so sometime down here. So you hit 92 microamps at 20 milliseconds, and so your time constant, RC, is 20 milliseconds. So RC is equal to 20 milliseconds, and so C is 20 milliseconds over 40 kiloohms, and you get for that 0.5 microfarad. So R was 40 kiloohms and 0.5 microfarad.